So I figured that as the new guy with the joint appointment between engineering and public affairs, where usually when I say I have this joint appointment, people are like, oh, cool. And then they think, and they go, wait, what does that mean? What I figured I would do is I'm going to sort of introduce at a high level a few things that I'm working on. So I'm violating a number of rules. I have way too many slides for the time allotted for me. And I'm going to not go into a lot of the details, although I'm sure there will be questions, and I can go into the details in response to your questions, all right? And part of that is because knowing the sort of pitching to the expected audience here, I think there's only maybe a few people who care so much about the Darcy flow in porous media, and you might have more of the sort of the policy and public affairs related concerns. So this talk is in 3 acts, okay? The first act is to frack or not to frack, all right? And then it'll sort of weave from there, and you'll see this gradual transition between the acts. But I want to start with Adila Hamideh. So a couple weeks ago, I got an email from this young lady. Turns out she's a junior in high school. And she asked me what my opinion of Conservapedia was versus Wikipedia in terms of their entries for global warming. Okay? So if I excerpt Conservapedia, global warming theory is a liberal hoax that the world is, I'm getting back to it, aren't I? Becoming dangerously warmer due to the human pollution of greenhouse gases. Liberals have used this theory of man-made global warming to seek rationing by government of life-saving energy production and consumption. Wikipedia says global warming refers to an unequivocal and continuing rise in the average temperature of the Earth's climate system. Since the early 20th century, temperature has increased about 1.5 degrees Fahrenheit. About 2/3 of this increase has occurred since 1980. Each of the last 3 decades has been successively warmer than any preceding decade since 1850. So I said, when I looked at Conservapedia, I was actually a little worried I might get some virus or malware or something by going to the Conservapedia site. But when I looked at it, I wrote back to her and I said, actually, I think it'd be better to talk about on the phone than for me to, to type out. And so when we talked, I said, well, what do you think? What do you think? And she said, well, I think it's biased. Good for you. So I asked her, we talked for a while, and I asked her what, if she could send me, she was doing a project for a physics class, actually, and if she could send me her project. And so she did. Here was her poster board project. There's me that's speaking with the professor, so I have my own plate on her poster board. And then she has this doing your part, okay? Now, within the doing your part, she came up with bullet points of how you can help, okay? First one, take shorter showers so you don't smell. The second one, unplug your chargers, quit playing with your gaming devices, go outside and do something instead of playing on your Xbox all day. Ride your bike instead of driving. It's good for you and you're helping out the earth as well as saving money. Read a book, a paper book, not a Kindle or a tablet. All right? You'll be off your phone and electronics, which means you won't need to charge them. Inform people about what's going on. Don't walk around oblivious to the facts. The last one is my favorite. All you germaphobes out there, use hand sanitizer. Don't keep on washing your hands all the time. So, the translation, if I was going to translate what Adela is saying, is use less energy. Okay? So, how are we doing on using less energy? Well, in 2005, I guess almost a decade ago now, the estimates were that from 2010 to 2030, we would increase our energy consumption by about 50%. Okay? and we'd increase our oil consumption to 124 million barrels per day. This is about a present estimate. This should actually be about a year ago. Present is defined as about a year ago. Estimates are that we are going to use only 300 to 330 million barrels. So the estimate was 340 by 2030, and now the estimates are that we're going to use less than that 5 years later. And instead of 124 million barrels per day, 110 million barrels per day of oil. So what happened? In 2005, the Energy Policy Act exempted hydraulic fracturing from regulation under the Safe Drinking Water Act. Okay? Hydraulic fracturing is extracting, it's a process that you can use to extract natural gas from shale deposits. In 2000, shale gas, the production provided only about 2% of our natural gas production in the U.S. And about 2005, it was about 2 billion cubic feet per day. 10 years later, it grew from 2% to about 23% of U.S. gas production. A couple of years ago, it grew to 26 billion cubic feet per day. So it was roughly a 13-fold increase in 7 years. Now, if you plot the shale gas, or the natural gas production in the United States, this is the conventional, this blue here is the conventional production, and the red here is the contribution from shale. So you can see conventional production was tapering off, or it was decreasing, and shale has really added a lot of production. So right now, the U.S. is the largest producer of natural gas. We, together with Canada, we supply roughly a quarter of the global supply of natural gas. Liquid natural gas import terminals are being retooled into being export terminals. And there's a variety of other consequences as of the production of shale. One of which is that natural gas prices have really decreased a lot. Okay. Now, don't look at your bill from this past winter because demand and the polar vortex and all that good stuff. So natural gas prices have really reduced a lot. This is residential. This is at the wellhead. Partly associated with that is the amount of electricity that we've been generating. This is from coal. This is 1950, and this is from coal. The amount of electricity being produced from coal has really tapered off as well. And what's happening is there's a shift going on in the generating mix. There's increasingly more electricity being generated by natural gas than it is by coal. Okay? And that's a good thing, because natural gas is cleaner than coal. It produces roughly half the amount of carbon dioxide emissions per unit of energy when combusted. Now, so to get to Adela's recommendations for what to do our part, what we should do in order to save us from ourselves in terms of the climate, we clearly, what she was talking about basically was using less energy, and that would fall under energy efficiency measures. So what I've got here is a projection. There's all sorts of studies that look at what you need to do in order to stabilize the atmospheric concentration of carbon dioxide, the most worrisome greenhouse gas, at levels depending on how they baseline it, but basically at levels that we think that we can possibly stabilize it at to reduce the possibility of severe disruption to the way we live our lives. Okay, and it's usually by 2100. Okay, so basically, this one is saying if we do nothing, these are going to be our emissions trajectories. To stabilize at 450 parts per million of carbon dioxide in the atmosphere, we need to be on this trajectory. Okay? And so these studies, what they do is they basically look at, well, what technologies can we or should we deploy? And these are usually cost minimizing, okay? In order to continue to provide the energy that we need and use for our society, but to do it with less carbon dioxide emissions in total. So there are things like adding or increasing the amount of nuclear electricity generated by nuclear power, increasing the amount that's generated by renewables. And this production of natural gas fits into this by the fuel switching, right? We are switching from a more carbon dioxide intensive fuel to a less carbon dioxide intensive fuel. So holding everything else constant, that should contribute something. Now, there are more benefits to using natural gas than coal. Not only do you get about half the amount of CO2, you get 0.1 pounds of sulfur dioxide per megawatt hour from natural gas, as opposed to 13 pounds per megawatt hour from coal. You get about a quarter of the nitrogen oxides emitted. You really don't have any particulates or mercury to worry about, and so on. So part of the reason I wanted to focus on fracking a little bit is it's salient, right? And there have recently been some forums. I think one is, "Are we fracking our health?" or something like that, which was just happened at COSI. It's about to happen.
It's about to.
It's about to happen. Okay, yeah. So, and there's a lot of opinions about fracking. And so there's clearly some benefits, right? Natural gas prices have decreased. Having access to cheap and affordable electricity or energy in and of itself is a good thing, right? Having less CO2, less sulfur dioxide, less particulates, less mercury emissions, and so on, in and of itself is a good thing, right? But there are concerns about the processes employed in the hydraulic fracturing. Mostly, or a large part, are the fugitive emissions. Now, when you are liberating this natural gas, you're producing methane, which is a much more potent global warming greenhouse gas than carbon dioxide. It's about 20 times as bad in terms of heating up the Earth when it's in the atmosphere than carbon dioxide is. Now, if you were able to do this fracking process and capture all the methane, that'd be great. But there's concern about fugitive emissions with them leaking out. Some people are apparently lighting their faucets on fire because there's methane coming out of their faucet, and they're putting a match underneath and saying, "Hey, look, this we have natural gas seeping out." But basically, the major concern is leakage from the system. When you're producing natural gas, you're then transporting it, distributing it. You have all of these pipelines, right? And the leakage from this system, it turns out to be very, very uncertain. And there's a paper published, I think, last week that basically says we don't know that much, and it's potentially alarming in terms of how much methane is being lost in the system. I'm working with a master's student at Johns Hopkins on quantifying for Michigan, Ohio, Pennsylvania, West Virginia, the amount of natural gas that is leaking from the pipeline transmission and distribution system. And the reason for focusing on these states is because that's primarily where the natural gas by fracking is being produced. So by expanding the amount of natural gas that we are producing in these areas, that's going to have to be transported and distributed, right? So the age of the system is a problem. And it turns out in Michigan, apparently Michigan has one of the oldest systems. They have the Antrim Shale, which it was started to be developed. And they actually have a policy in place to help subsidize, or policy available to help subsidize replacement of old infrastructure. So what the student is doing is looking at how that might work. And I said, well, can we quantify how much we need it to work? Okay.
You're talking about distribution, not production. distribution of existing natural gas.
Yeah.
Jeff, I have a question.
Yeah.
Transportation, so as you mentioned earlier, the conversion of these LNG import facilities into export facilities.
Yeah.
And this, even before this happens, there's a global security dimension to this. All the production capacity that LNG exporters were developing a few years ago, when in 2004, Chairman Greenspan was warning about impending shortages and all of this, and so we built these facilities. Well, then there were the export facilities in the Qatars and Venezuelas and so forth. And now, even before we export, the LNG is being channeled to Europe, and so the Russians a few years ago were forced to accept spot pricing, which is cheaper pricing than for the gas that they deliver to Western Europe. And that's only the beginning of this, but it has to be transported in ships. I was wondering if anyone is looking at, not that I think it's that big a deal, mind you, but the escapage of methane as you liquefy it, put it on ships, and then regasify it in the. Is that actually being studied?
This paper is in Science, and basically they looked at as much as they could across the supply chain, and basically and
even exports.
I'd have to look back at the paper, but they looked at all sorts of infrastructure and transportation-related issues. So I don't remember exports.
Yeah, my sense is of this sub-literature is that they're not looking at that too much. But
yeah, this one I think is the first one to really take a really systemic, holistic look at it.
Yeah.
Yeah.
Explain the discussion you just had.
Can I do what?
Explain the discussion you just had.
You want to explain this?
Okay.
I'm gonna get pizza while you do that.
Well, I'm an economist, so when I say this is going to be short and clear, I'm lying at least once. So you have, as Jeff pointed out, commercial shale energy production began about 15 years ago, and that followed a long period of innovation of combining the horizontal drilling technology with the fracturing technology. These technologies have been around for a while. So George Mitchell, not the former senator, but the petroleum engineer, was instrumental and took the lead in putting these things together. And anyway, but there was the limited impact for a while on the natural gas markets, and our sense of what natural gas supplies were, again, that's indicated by the Greenspan quote from 2004. But over time, I mean, the shale is all around. Jeff, you probably know the geology better than I do, but they're the remains of ancient ocean beds. And basically the source of all of our hydrocarbons. The thing is that 90% of the organics or the hydrocarbons that were originally in that shale are still there. So this is the mother lode, and it's all over the world. That's why people like Jurgen and others no longer use the term peak oil. This is a massive, massive resource that started to be developed here because of the Natural Gas Act in 1978 and so forth. But our country is, I don't know, Jeff, are we already exporting gas from Alaska down to Asia where gas, if we aren't, we're about to.
Yeah, I'm not sure, I don't know.
Then the next step is going to be to export natural gas from the Gulf to Western Europe and so forth. And there's no doubt that we're just about at the point where our production equals consumption. Alaska is sort of separate, of course, but the trend, and in terms of additions to reserves, Jeff had a very helpful diagram there. We're adding reserves much faster than we're depleting this. And so this is, as they say, a game changer. Does that address your question? And with the price impact, the ultimate beneficiary of all these technological improvements is the consumer in terms of lower prices. Since 2008 or so, the price of natural gas is decoupled from the price of oil. So it's been low and stable, notwithstanding this winter with the heavy demand.
What's your question about where the leakage occurs, whether it's from extraction or your point was you've got this global supply network?
Well, it was a minor point that you have.
satellite-based stuff that detects methane fluxes and things like that. So
Just a minute, short and clear?
The point was that we could hear it, that's all.
Okay.
This discussion sort of preempted a few of my slides, so a little bit. But there are some worries, right? We are concerned about the potential for groundwater contamination. There's clearly a change occurring, mostly in rural areas where the shale development is occurring. And there's concern about health impacts of hydraulic fracturing. I'll get into this a little bit more. So what is hydraulic fracturing? What are we talking about with shale or unconventional natural gas and oil production? Well, so it's been enabled by the ability to now drill. We're used to vertical wells, right? We can now drill down and steer the well. Okay, and these shale layers tend to be relatively thin. And typically, when we talk about producing oil or natural gas, we're drilling a well into a place where shale or another very impermeable layer has trapped the migration of these fluids. Okay, so natural gas and oil, they'll flow, right? And due to the strata in the subsurface, they've accumulated into economically viable deposits, right? Often they accumulate under shale, which is very impermeable. You can't really get stuff out of it that easily. So this is this new resource that's now being opened up by our ability to directionally drill and use these techniques where you pressurize enormous volumes of water, inject it into the directionally drilled well to break apart that shale, okay? To break it apart, to create pathways for the natural gas and the oil to flow, right? And what's injected in here, in addition to a lot of enormous amounts of water and some chemicals I'll talk about, are little proppants. They're pieces of sand, basically. And some people actually apparently use coffee grounds. But what happens is when you fracture this, these cracks open up, but the pressure is so high under there that it wants to close back up. So these little particles of sand wedge it open, right? So it props it open so then the natural gas and oil can flow. So people are concerned about these fractures liberating this natural gas and then the fugitive emissions of natural gas just percolating up to the surface and asphyxiating cows and things like that and humans, right? So like you started to say, we can produce oil from shale as well. And so if we go back to, I think this is 1920, I can't quite read it. Doesn't matter, a long time ago. Our oil production peaked around 1970, there's another burp around 1980. Yeah. And then the mid-2000s, our oil production really started to ramp up. Okay? Correspondingly, our imports really started to bend over. Okay, right? We're producing much more domestically, we're importing less, right? And we've now at the point where we are now producing a little bit more than we're importing. So we are a net producer of oil, which has all sorts of geopolitical ramifications. So basically the landscape has changed. That's all of this is just to say, sort of like what we just said, the landscape has changed. And how is it changing? We've now opened up all of these areas which conceivably we can get oil and natural gas out of, right? So the Marcellus, primarily in Pennsylvania, is being widely fractured. The Utica here in Ohio is starting to be fractured as well. And these are often places that are either quite rural, you can't really see this, but this I took in eastern Ohio near Zanesville. But they're often in quite nice areas. So like I said, in 2005, the Energy Policy Act exempted hydraulic fracturing from regulation under the Safe Drinking Water Act. There are also a number of other exemptions and exclusions, things from the Resource Recovery Act, Comprehensive Environmental Response Compensation Liability Act, and so forth. So part of the reason that hydraulic fracturing has been able to go forward, the technology was there, it was ready. We could directionally well, we could fracture things. We've been doing it for decades. But by exempting it from regulation, that allowed the operators to go forward, and we've had all those positive benefits. Is part of what I was getting at, right? But one of the problems is that it takes a lot of water. Okay. And there's essentially three ways in which the water is involved. There's the fluid that you're injecting. There's the wastewater that happens just out of the drilling and normal production. And then there's the flowback water, which is basically when you're pressurizing this water and you're shoving it down into a place that doesn't want it, it backwashes it back up. Okay, it's fracking backwash. Okay. And about 30% of the water that's injected stays down there, so about 70% comes out. What comes out is full of a bunch of chemicals and stuff, some of which went down there, but also is pulling out nastiness that's down there already. So all sorts of other hydrocarbons that aren't oil and natural gas, radioactive substances like barium, strontium can be present. And so forth. So this flowback water is a big concern. Okay? And the disposal of it, because it's pretty nasty stuff, you can treat it a little bit, maybe reuse it, but by and large it's being disposed of in deep wells. So Pennsylvania is going gangbusters fracking, right? But their geology is not such that it can contain the disposal of the fracking of the flowback water. Right? And so where's that flowback water being disposed of? It's being shipped over here in Ohio. Okay.
Just out of curiosity, the past 2,000 years in the amount of fresh water available on the globe hasn't changed. About 3% of all water is fresh water, and about 2/3 of that is tied up in the ice sheets. So
increasingly less are tied up in the ice.
Yeah, that's true.
Ask Adela, she'll tell you all about that.
Would it be possible to pressurize the air? I don't know. I'm sure engineers have tried, but
yeah. So the part of the issue, I'll get to the next. I think the next. Okay. Yeah. So there's a large number. I'll address that in a second. A large number of potentially harmful constituents in that fracking that's being injected, and these have purposes. There's biocides, breakers, cross-linkers, gelling agents. You can't really stick all that into air. So the water is basically carrying all these chemicals that are necessary for the the production, including the proppants, the sand, right? So there is research looking into using carbon dioxide to do the fracking instead of using water. Because basically, it's a consumptive use of a lot of water. Right?
How much, Jeff? Because what I understand from Western Pennsylvania, all the fracking sites in Western Pennsylvania, like Washington, PA, and so forth, the rough number I heard from a colleague at Carnegie Mellon is it's comparable to about 10 to 15% of the water use, domestic water use in Greater Pittsburgh. Now that's not consumptive use, I grant you. But,
right.
But
yeah.
So 10 to 15% doesn't sound huge. It said a lot, but
yeah.
How much is it?
I haven't normalized it by that. I do have tons of data on this, and I have only one student. So this is also breaking. There was also partly an advertising.
you need a lot of students.
I need a lot of students. Yeah, listen. I need a lot of students to help me, work. So I have 1 million records of fracking jobs in the U.S. What's been injected, how much water, what's been disclosed, where. Some of it I have production data, but in large part it's about up to and exceedingly and even more than 10 million gallons per injection. So I haven't normalized it by those consumption of the city, but I can do that, or a student could do that. So anyway, so all these constituents that are injected, they're being thrown down there for a reason. Things like making sure the bacteria doesn't follow per one frac job, 10 million and more gallons per. So you can refrac. You can.
And how many sites?
Oh, I should have, there, I have about 4,000 in Pennsylvania. I think I have right now about, well, I just downloaded this a couple weeks ago from the Ohio Department of Natural Resources. I think I have about 100 or so. But that's basically
a lot of zeros.
a lot for the water. Yeah, so when you multiply all these sites and the growth, the exponential growth, right? So I was actually playing with what Act 3 would be, and I chose to take out the energy water part and put in something else, but I can talk about it.
Is there any variability in the price of water losses?
Not really, because what they're doing is they're taking it from groundwater. They're just, what they do is they I have other pictures from that one site. They have a big retention pond, so they pump water, and put it in a retention pond because they can't pump it fast enough out of a well to do it as they need it, so they hold it. So they simultaneously pump it from a well and discharge their retention pond at the same time so they can get all the water down there as quickly as they would. No. The retention pond is fresh water. It's potable water.
They are recycling water. There's research in this.
Yeah, they're working on trying to be able to reuse the fracking, the flowback water. And there are some, depending on what's in it, you can in some places treat it. There's a really nice paper on this, but it also gets into all you can do all sorts of network analyses on community disruption and where the water trucks are going to these rural places, and then where they're taking the nasty stuff away for either treatment or deep injection for disposal. So, what I've been looking at with one of my colleagues at Minnesota, because as most of you know, I was there before I came here, and I can't bring that money with me because it's an internal grant. So we've got two students there. Professor Betsy Wattenberg is in environmental health sciences. She's a toxicologist. So we've been looking at how hazardous the constituent, how this fracking fluid might be to human environmental health. And one of the things that I want to look at is who's reporting what and where. Okay, so one of the issues is that operators are not necessarily required to disclose what they're injecting. Okay, now in North Dakota, where we've been focusing, because Minnesota's right there and it's a neighbor, they allow for a proprietary exemption, so you don't have to report everything. You can say it's business confidential. You can say, I have the mixture for Coca-Cola, and you don't get to know what it is. Right? So, what we've been looking at are these toxicological endpoints for carcinogenicity, neurotoxicity, acute toxicity, all sorts of stuff that can mess us up. Whether it's orally, through oral routes, through inhaling it, or contact with irritants and so forth. So in North Dakota, we have about 3,200 wells, 223 unique chemicals that we can identify, and 16,000, almost 16,500 entries that are proprietary, so we don't know what they are. Okay. Now, there's no standard, right? So what one company reports and says, hey, this is ethylene, another one could be listing as proprietary, okay? So part of the question that I would love to have a student work with me on is we can map these, right? We can spatially see where demographics are, where surface water is, all that stuff, and say what are they reporting and where, right? And how might that be different in different locations? So this is our big database, and all this is really to say is that when we know something about one chemical, we tend to know a lot about it because it's been studied. When we know nothing about a chemical, we either know everything or virtually nothing. So we can say, okay, it's carcinogenic, it's not acute toxicant, it's not a respiratory irritant, or we can say we don't know anything. Okay, and it turns out that about I think our latest numbers were about 40% we know a lot about, and 60% we don't know much about. Now, there may not have been a reason to study these things in the first place, but things like ethylene glycol is one of the things being injected. That's antifreeze, right? You don't want your dog to drink it. We probably don't want to drink it either. Right? So it turns out that in terms of some of the concerns about groundwater contamination and health hazards, on the fracking fluid side, it's really about the occupational health. It's about occupational exposure of the people who are working. Now, when I was at that site, they weren't wearing respirators. They, there was a cloud, and that was, they were offloading the proppant, the sand, and that's an inhalation carcinogen, right? They were wearing coveralls, but I think those were to protect themselves from getting dirty, not to necessarily protect themselves from the chemicals that they were working with. The disposal of the flowback water. So in terms of groundwater contamination, I think some of the initial concerns were about the drilling and the propagation of the stuff that's being injected down up into the groundwater aquifers. That's not really the concern. The concern about groundwater contamination or drinking water contamination is from this flowback water and spills and the disposal of the flowback water.
Jim, how's the proppant carcinogenic with sand?
When you inhale it.
Just with silica in there?
Yeah. So overall, so that's sort of one.
But is OSHA, on your list of regs that were exempted, OSHA stuff is on there?
No, so I'm not sure what the site requirements are. That was about the process, right, and the operations. But I mean, we've looked at all MSDSs and material safety data sheets and so on. So, sort of closing Act 1. It's an example of how of the research that they do is basically how do we transition the energy systems from those that we have to those of the properties we want, such as less CO2 emissions, right? Such as using less water per unit of energy if possible, such as keeping the energy affordable and reliable and so on. So these broad questions, how do we organize society to enhance energy sustainability, those are sort of broad overarching questions under which there's a variety of questions that I'm working on, including one that I want to work on that you perked up. You were scribbling down that disclosure one. So the thing is, we use the subsurface a lot, okay? So prior to coming here, I know this might be taboo, I'm talking about Michigan, and I should put in, oh, I don't have Michigan up there. Oh, I do, there. I'll put an X right there. We did a project focusing on Michigan and how their subsurface is used. Now, if you think about it, you can categorize the way we use subsurface. We get water from it, we get energy from it, we get metals, minerals, diamonds, gold, all that stuff from it. We store energy down there too, and by natural gas, seasonal natural gas storage. And we also dispose of waste, like we're disposing of the flowback water with these deep injection wells. So we use the subsurface for a lot of things. And one of the questions is, we're increasingly going underground with what we're doing. So how do you coordinate all those activities? How do you think about this in an integrated way? So coming back to what I would say we need to do in response to Adela, we have to deploy a wide variety of technologies. So just essentially fracking is essentially a fuel switching technology. There's this thing called carbon capture and storage, which virtually every estimate up until a couple of years ago said we need to, about 20% of our reduction in carbon dioxide emissions has to come from this thing called carbon capture and storage, this technology called carbon capture and storage. So what is it? You stick a device on a power plant, you separate out the carbon dioxide from the emissions before it gets in the atmosphere, you pipe that carbon dioxide, you inject it underground into these old oil fields, deep setting aquifers, old oil reservoir, natural gas reservoirs, where essentially either there's stuff down there that we don't want, like this really nasty water, or we've taken oil or natural gas out, we're just putting another fluid back in, okay? So, more recently, the projections are saying it's even more dire. This carbon capture and storage stuff, we need it. If we're going to stay on the trajectories we're on in terms of development and improvement in technology and energy efficient, we absolutely need it in order to rescue ourselves from the climate. Actually, the phrase is to have a 50% chance of avoiding dangerous anthropogenic interference with the climate system by 2100. They're down there, so wants to rise. So if it reaches a fault, fracture, a well bore or anything, it could leak its way back up, okay? Also, carbon dioxide, when it mixes with water, you have essentially carbonated water, right? You've heard these things, if you stick a tooth in a coat for 7 days, it'll dissolve, right? There's these chemical reactions that can happen. So you've got this carbonic acid, which is a weak acid, which can cause geochemical alterations of the layers that are impermeable, which we are also now fracking, which were intended to contain the buoyant CO2. So there's all these potential conflicts in the subsurface. So again, you inject carbon dioxide deep underground, there's this buoyant CO2 plume which could reach potentially another well where it might leak up and get into overlying layers and maybe potentially hit groundwater. What also happens is when you inject carbon dioxide, there's this big pressure pulse in the native fluids that are down there. And that pressure pulse could push brine, this really nasty water, up through leakage pathways. I'm just showing wells here, into these overlying aquifers. And so the concern then would be about if we contaminate groundwater either with CO2 that's been that's migrated out or brine that we've pushed out through the injection operations. Okay. So if we look at Michigan, just to sort of give us a sense for how much we mess with the subsurface, there are about 30,000 active wells in Michigan. Roughly a third of them are for natural gas production, so they're color-coded by different things. Red is natural gas, blue is oil. These are different layers underground. If you add on all the plugged and abandoned wells, all the ones we're no longer using, there's another roughly 30,000, about 45,000 wells that penetrate deep into the subsurface. This does not include the 400,000 wells that are getting drinking water out of the top layer here. So there's a whole bunch of potential pathways for stuff to leak out, right? Now, within Michigan, there are 16 hydrostratigraphic units. These are the units here. Here's again the cross-section of all the wells. Now, where we're talking about injecting is way down here in the Mount Simon or the St. Peter. Right here, it's about 1.8 kilometers below ground, so it's pretty deep. Okay. And again, you inject carbon dioxide here, pushes out native brine. CO2 is buoyant. It could find a way potentially to get up to groundwater, right? And that's a big concern. So EPA is in charge of protecting ourselves from ourselves, right? And they've established a new type of well under the Underground Injection Control Program, basically to protect underground sources of drinking water. So if you do the comparison, fracking, exempted, CO2 storage, not at all exempted. In fact, there's a very modern regulatory system being applied to carbon capture and storage. Part of it is to define an area of review. Now that's the area when you inject, you get the brine that is, or you get the CO2 that's buoyant, you get this pressure pulse. Anywhere that something could leak out and potentially get to groundwater, that's the area of review, okay? The Department of Energy says, we understand we might not have a perfect containment system down there, but our goal is to have 1%, at most 1% leakage out of these storage reservoirs. So some of the questions I've asked is, well, how likely is it all of that stuff is going to get all the way up there, right? If it's so deep, right, how likely is it going to get up there? And really what I'm interested in is, can leakage be beneficial? If you think about it, you got this pressure force, this driving force that you're messing with down there, right? You are creating pressure down there. If something leaks, it releases pressure, right? So can this pressure release actually be beneficial? Yeah, so this is Western Michigan. So here's the mitten, we're over here. Picked a spot here where the geology is really great for CO2 injection. There are two coal-fired power plants relatively close that together, if you cap the amount of capturable CO2 is about 9.5 million tons of CO2. This is an enormous power plant. We really don't have many 1.6 gigawatt power plants out there. So doing some simulations of injection and leakage and these plumes and how the pressure goes out and finds all these leakage pathways and stuff. Using probabilistic stuff for how the subsurface properties are in the geology and the permeability and porosity and the temperatures and all that stuff, as well as how leaky these pathways might be. So here are all the wells that are in this area, and I've highlighted the ones that go down all the way into the Mount Simon that are primary leakage pathways, okay? And so these wells, if they leak, will have some sort of effective rate at which they leak, and that's essentially determined by the leakage permeability, okay? So it's basically, it's a big probabilistic sensitivity analysis, drawing from distributions and all that stuff. So down here, 1,800 meters below ground, this is where we're injecting. Up here is the groundwater aquifer. Injecting 4, 12, and 10, and 20 million tons per year. So it's roughly twice the amount of CO2 in blue that is produced by those 2 power plants, a little more than that's produced by those 2 power plants, and roughly twice the amount that's produced by those 2 power plants. Assume every well in the basin leaks, okay? You're citing this, one of the reasons why it's located right here is there are 8 wells that go all the way down to the Mount Simon. Okay, so this is a stupid place to locate it, really. The geology is great, but you got 8 potential leakage pathways there. Add to that, all these wells leak, okay? And so, and the distribution, it's a uniform distribution that goes into like extremely ridiculously leaky, okay? So you do this injection for 30 years, it's leaking the whole time, all the wells are leaking the whole time, you don't stop injecting. By the time the carbon dioxide gets up here to the groundwater aquifer, it's about, well, depending on which one, maybe 20 to 30 tons per day are getting into the groundwater aquifer. Those green dots are places throughout the world where carbon dioxide is naturally seeping out of the earth, okay? If you do some extrapolations, because we have data for the surface, for the natural analogs where it's seeping out, and we can only model to the groundwater. Basically, we expect that in this ridiculously, stupidly sited place, the amount of, and you don't stop even after it's been leaking for 30 years, the amount of CO2 that's going to get out of the subsurface, released from the ground, is much less than these places where it's already leaking. Now, of these places, there's only one person who's been killed that we know of because of CO2 leaking out. That was at Mammoth Mountain, California. And the reason is that's in a valley, okay? And carbon dioxide, while it's buoyant down here, by the time it gets up, it's heavier than air. It's more dense than air. There was a hiker who decided he needed to camp for the night. He found this clearing in this valley where there was no vegetation. So he set up there. Why was there no vegetation? Because there was carbon dioxide coming out of the ground. He basically, fell asleep and never woke up due to his chosen location. But carbon dioxide mixes really well in the atmosphere. It mixes quite readily. So you need a valley, you need no wind, and you need to sleep on top of it, right? So getting to this 99% storage permanence goal, okay, I just want you to focus on this curve here. Now the diamonds are 4 million tons, the triangles are 12 million tons, and the circles are 20 million tons. DOE says we want at most 1% to be allowed to leak out. So if you look at the insight here, here's the 1%. What do you got? The first year in this scenario, 4 million tons violates this 1% right away. The 12 million tons, takes 5 years for it to violate it. The 12 million tons takes 3 years to violate it. If you calculate 1% of 20 for 3 years versus the small amount that is coming out relatively for the 4 million ton, basically because it's a percentage-based regulation or goal, 50,000 tons leaking out is bad, but almost 600,000 tons leaking out is still good. Okay. So maybe we should consider how we go forward. Okay. So remember I said, can leakage be beneficial by reducing this pressure drive? So you don't really need to look at the details of this, but just look at the green relative to the red. If the green is bigger than the red, that means the probability of CO2, so the green is the probability of CO2 being present in a place being reduced due to leakage. Red is it was increased, okay? So this is a scale from 0 to 100%. So basically the key is, if the green bar is bigger than the red bar, then leakage is reducing this area of review, okay? It's reducing your likelihood of the area over which you might contaminate groundwater, okay? So what's plotted on top of here is some averages and standard deviations and all that stuff. But the answer is basically yes, leakage can serve a beneficial service by reducing the area of review. So, okay, Act 2.5, all right. So we've talked about carbon capture and storage, we've talked about fuel switching, renewables, another 20%, right? Well, what if we can combine these two? We can inject carbon dioxide and use that carbon dioxide to some beneficial purpose. Part of the reason, aside from a really modern and restrictive regulatory system, part of the reason why we haven't done much of the CO2 capture and storage stuff, there's no business case for it. You're just sticking it down there, right? You're not making any money with it, you're not avoiding a tax, right? An emissions tax. So let's combine carbon capture and renewables. Let's inject that carbon dioxide, let it pick up the geothermal heat when it's down there, produce the hot carbon dioxide, run that through a power plant, pull the heat off, convert it to electricity, stick the cold carbon dioxide back down there. So you basically have a carbon capture and storage operation where you're siphoning off some of the carbon dioxide. Okay. Well, if you do that, it turns out the carbon dioxide extracts heat much more efficiently. Due to density contrast and the buoyancy of carbon dioxide, it gets hot, it wants to rise up, it wants to produce itself. When you make it cold again, when you pull the heat off, it's less dense, you gotta shove it back down. It generates a self-convecting thermosiphon. Yeah?
You need more efficiently. Water is circulating.
Yeah, I was Control-Zing a couple times. Actually, as a side note, Control-Z was the best invention ever, right? When you accidentally delete that thing, I remember the days before I was Control-Z. Anyway, so yeah, more efficiently mines heat than water, right? Then conventional approaches to producing electricity with geothermal heat. So since it's more efficient, you can use a lower temperature resource. So all of our geothermal power plants in the US are in Nevada and California. We can basically come almost all the way to the Mississippi River and still conceivably have cost-effective energy production. Another thing is you can control the injection and the production. So one of the problems with deploying renewable wind and solar is that when the sun doesn't shine or the wind doesn't blow, the electricity doesn't flow. I didn't intend to say that. But yeah, so you need, and so you don't necessarily get the electricity when you want it or when you need it. You can control these production and injection schedules so you can levelize those fluctuations. So essentially what we're talking about is using a fossil fuel feedstock to produce renewable energy and enable other renewable energy. So to wrap up, talked about shale, talked about CO2 storage, quite different deployment trajectories, right? Partly due to policy, right? There's potential conflicts there. Like I said, we're fracking the layer, we want to store the CO2 underneath. But you can also inject carbon dioxide to store it in shale. So emerging work, and I have a proposal in on this, is to say, let's inject the carbon dioxide as the fracking fluid instead of the water. And what it does is it preferentially adsorbs to the rock and liberates methane. So it's not necessarily a pressure-driven production, it's a swapping. CO2 geothermal that I just talked about, right? So there's all these sort of technological recombinations that can occur. So how can we coordinate all of these? Okay, so now I'm going to Act 3, or stepping back a little bit more. Now we think about how we use the subsurface. Are you guys familiar with the Millennium Melling, ecosystem assessment? No. So the ecosystem, there's services that are provided by the environment, right? Like bees pollinate, wind pollinates, right? It blows pollen, water gets naturally filtrated, right? So there are all these services that if you were able to price them appropriately, then conceivably we would conserve them more, or we would, in our consumption decisions, right? So there's a lot of effort to say, all right, let's figure out the value of these non-market services. So let's go back to how we use the subsurface for all these things. I think there's an analogy, right? We use the subsurface for a variety of different purposes, right? We get the energy, we get the water, we store the waste, we get metals, minerals, and all that stuff. The ecosystem services people have separated them into 4 categories of these services. Now I'm going to apply those ecosystem service categories to what we do with the subsurface. Okay? So provisioning services, that's the stuff we use directly, right? Those are the fossil fuels, the water, the heat, and the metals, and so on. The regulating services are things like it can transfer heat, it can transport mass, okay? It can filter and purify water. It can contain the wastes that we don't want on the surface anymore. We inject down there, it provides this containment service. Supporting services, these are these long processes like plate tectonics and all that stuff. It's characteristic of the earth that produces those services that we then rely on. Okay? And we also use the earth, like I like to go to the mountains, right? Why are the mountains there? Because plates collide, they go up, and we can look at the nice mountain, right? So visual backdrops, I like to go hiking. You know, some people go to the mountains to find themselves, right? Personal adornment, we wear gold, right? Where we get the gold, we get it from the subsurface. Personal milestones. Personally, I like these baseball diamonds, but we also have those sorts of diamonds that we get from the subsurface, right? So we're using the subsurface in a variety of ways. We have occupational identification. I'm a coal man, I'm an oil man. We have political pride, where coal is the state rock of Utah, but it's the state mineral of Kentucky. And a rock and a mineral are 2 different things, and I'll let you assess which one of those states got it wrong. All right, so back to everything. These are the overarching questions under which I have a variety of research questions. Thank you. Any more questions?